All right, and welcome back, everybody. So last time we looked into a preliminary analysis of the Lorenz system, and now what we'd like to do is see what other kinds of techniques we can employ that are beyond our usual toolbox that we remember from the phase plane, and see if there's any more information we can glean out of the system just from a cursory analysis. And the first thing that we will notice is that I need to go back to MATLAB Mobile. Oh, so we disconnected here. One moment. Pay no mention to the man behind the curtain. So what we noticed last time when we picked up the Lorenz attractor when we were modeling this system, we noticed, and we give that another few seconds, we noticed that this system had a certain amount of symmetry to it. Right, and what I can actually do here is show you that this is symmetric across the plane x minus y equals 0. So in other words, where the x and y coordinates are the same, that is the symmetry that we see. And in some sense, if we had a dividing plane between the two lobes of this guy, that's exactly what would divide our system. So let me go back here into the notebook and show you that there is a rotational symmetry in the system corresponding to flipping both the x and y coordinates of a solution. So sure enough, we can see that if we had a solution and we flip the signs on the x and y components, then the derivative in the x and y components must pick up a minus sign as a result. Right, just by necessity of the fact that we negated both of those pieces. But on the right-hand side, we're going to have sigma times a y minus x, but we're replacing y and x by negative y and negative x respectively. So we wind up switching the difference here. It's going to be x minus y, but we picked up the negative sign on the left-hand side of the equation, which we can go ahead and use to negate this guy on the right. So sure, the x dot equation is satisfied when I negate the x and y components. Let's see what happens in the other parts. I can do the same thing with the y, right? Y dot will pick up a negative sign, and I go ahead and substitute this in, and I can see there's really not too much going on here. I just factor out the negative sign from all three of these pieces, since there's exactly one new negative sign per term in the y dot equation. Now comes the tricky part, because I don't actually negate the z component, right? I didn't change the z. However, I am negating the x and the y terms that show up here, which means that their negative signs cancel out, and I wind up with, you guessed it, the original xy minus bz z dot equation. So that means that the components of x minus here, right, the solution x minus that I named upstairs, is also a solution to the equation. So if I have a solution x, then there is kind of a rotationally symmetric pair or counterpart that comes with that solution and is also a solution to the system. So as a corollary, every solution to the Lorenz system either is rotationally symmetric about the z-axis or has a rotationally symmetric partner that is symmetric, that you can find by rotating 180 degrees about the z-axis. Now, we notice that in particular, because of that rotational symmetry, we're going to see that it's the z-axis itself that is the only rotationally symmetric solution for this system. Or it's the only one that is self-symmetric. It actually has a point symmetry group associated with it. So notice that the z-axis is invariant, and you can check this directly by substituting x and y both equal to 0 into the Lorenz system, and you'll wind up with the z being the only term that changes, or the only component of the solution that changes over time. X and y are both going to stay 0 for all time. So that means that our solution could only move along the z-axis, so the solution, or the z-axis, is an invariant subspace. And we can actually see what happens when we project along that invariant subspace. So we take a solution, and this is what I did. I actually took the solution for initial conditions 0, comma, plus or minus 2, comma, 0, and I sent them through my MATLAB software, my MATLAB script, to see that there is a very striking rotational symmetry in here. And you can see that wherever there is red on the left side, there is blue on the right, and vice versa. Wherever there is blue on the left side, you see red on the right. So this guy definitely has that rotational symmetry that we just showed. Okay, so this is a nice way of visualizing solutions in the plane. You can just go ahead and take your solution and project it down into the xy plane along the z-axis. Okay, so we have rotational symmetry. That may not be something that's in our back pocket that we think about, but it's definitely something that we notice in the simulation and we would like to demonstrate on paper. So we did. What else do we notice? Well, you might notice that all of my solutions want to come toward this surface, this butterfly surface, the attractor that we called it. So let's show that solutions want to go toward that butterfly. And what we're going to do in order to establish that is it's going to happen in two stages here. First, we're going to establish that solutions want to get within a certain region, that they want to be drawn into the interior of an egg-shaped region, an ellipsoid, centered at the center of that butterfly. And once we have established that solutions want to flow into that region, we are then going to show that solutions want to lose volume. They're going to start to shrink wrap around that butterfly. So let's start with step 1 and then string them all together. We'll do step 1, we'll do step 2, and then we'll string them together to make the complete argument. So we're going to create a version of a trapping region, and this isn't going to be the same as it was for the Poincare-Bendixson theorem. Right? We're not trying to come up with an annulus or a punctured sphere, punctured ball region, nothing in the sense that we're trying to find a limit cycle. What we are going to do here is show instead that solutions outside of an ellipsoid, a very particular ellipsoid, want to come into the ellipsoid. And once they are there, they will need to stay there. Right? There's no way for them to leave this elliptical ball. And this is what I'm affectionately calling a trapping region, but it's really more of an attractor in some sense. It is trying to keep solutions inside, but I'll reserve the word attractor for the next video. It's going to be a very specific definition, and I don't want to sully it with colloquialisms. So let's go ahead and talk about this proposition. Let's find that ellipse, that there is an ellipsoid centered at 0, 0, 2 r, such that all solutions, right, every initial condition that I want, must enter this ellipsoid eventually, and then remain there, remain within it thereafter. So there exists a globally attractive trapping region, and I will again put this in quotes because that's not the definition of a trapping region that we had for the Poincare-Bendixson theorem. So I want to make it very clear this is not the same, but in some sense, it's basically half of that definition. Also, we don't necessarily get the limit cycles or the attractive limit cycles that we're looking for. So to prove this, let's go ahead and take this function v, and in some sense, this is going to be like a Lyapunov function. We're trying to figure out, we're trying to show that solutions want to decrease this function along trajectories, or that solutions want to decrease this function as they move forward in time. So it might seem a little strange. Why would I pick this particular function? Just go with me here for a second, and you might see where we picked up these coefficients. It's a matter of trying to get certain cancellations in a dot product downstairs. So if I go ahead and set v equal to some constant, then the level sets, right? I'm looking at the level sets of this function, and either I'm using a constant that is not in the range of v, so that I don't have any points that go to that map to that number. So v equals -1 would fit that bill. So that would be an empty set. Or on a regular level, so if I'm not at the origin or I'm not at the height 0, any positive constant any positive level set here, or level set corresponding to a positive number for V, is going to be an ellipsoid, right? It's going to be this egg shell, so to speak. So, we're going to find a level, a level for this function such that the vector field on that ellipsoid is going to flow to the interior. So we want to check, is there a negative net outward flux on that surface sigma? This is exactly that half of the definition, the first half of the definition of a trapping region from the Poincare-Bendixson theorem, right? So we're just not showing anything else beyond that. We're just showing that solutions flow into the ellipse once they get there. So we recall, let's do this just like we did upstairs, that there is a normal vector field for this guy, and in fact I can show that the gradient of this function v is an outward normal vector field. It is not necessarily a unit, so I'm not going to say it's a unit field, but I could make it a unit field if I felt like it. I don't need to, so I'm not going to. So grad v is an outward normal field for sigma, and we can go ahead and compute, just like we did for the Lyapunov function in the previous video. We're going to compute this gigantic dot product, or maybe not gigantic, it's just cumbersome. And through a little bit of algebra, you can convince yourself that you wind up with the following, right? That you wind up with this as your dot product. And this is effectively going to be what happens, v dot. It's how solutions, how v changes along solutions, right? So therefore, we wind up with a whole bunch of squares here. And I'm going to pay attention in particular to the fact that this is a negative number out front, positive number, positive number, positive number, not so positive. So what we need to do is show that there is a particular parameter range or a particular choice of the constant for the ellipse that we can go ahead and guarantee that this guy, that this thing inside the parentheses is going to be a positive number no matter what. So I'm going to go ahead and say that I would like to define this function to be w and play the same game as I did before, where I'm looking for level sets that correspond to a different collection of ellipsoids. Now, why would I do that? Well, because what I want to do is figure out for which constants I get, so which parameters, which constants I get a globally attracting object, or I want to make sure that stuff is moving toward this object. Therefore, if the ellipsoid, and I'll call this guy epsilon, right, corresponding to w equals constant, is taken to the level such that this term here is positive, or maybe not that term. What I want to do, let me bring it over here. I'm looking to show that rx squared plus y squared plus b times z minus r squared minus b r squared is equal to mu, right? This is going to be my epsilon surface that I'm talking about, my epsilon ellipsoid. I need to make sure that this guy exists. All right, so once I do that, that'll be mu needs to equal, or needs to be bigger than, it can't be any smaller than a certain number. Do I have that right? I may have messed something up here. I'll double check my notes later. But the point is that there is only a certain variety, a certain range of values of mu that I can choose here. But suffice it to say that I can make this ellipsoid large enough so that it exists, and moreover, so that it contains the other ellipsoid. Right? In particular, what's happening here is I get one ellipsoid, right, and this would be the sigma, from my original analysis, or from my assumption up above. Like, I'm trying to demonstrate the trapping region here, and that's centered at 0, 0, 2r, so that means I move way down here and show that there is yet another ellipsoid, and this guy is going to be the epsilon surface that contains this guy. And what I want to make sure, sorry, not that way. I want this to be flipped, actually. I want this guy, yeah. So red should be in here, and blue should be out here. Because what's happening, I am guaranteeing that solutions are going to be coming into the epsilon region. So all solutions want to decrease so as to get to the epsilon surface. But once they do that, they have to go through the sigma surface to get there. And we've established on sigma that that if this is large enough, then this flux, right, that's what this guy is corresponding to, this flux term on sigma is negative, provided we use large enough ellipsoids. But little epsilon is trying to attract everything inside the bigger ellipsoid sigma. And that's exactly what we want. Once we enter sigma, we stay there. And that proves the proposition. So it looks very much like an argument that we made for when we were talking about trapping regions for the Poincare-Bendixson back in the day. But it's a little bit trickier in trying to make sure you have the relative sizes correct. So, final remark here. So, although this guy contains a trapping region for solutions of Lorentz system, solutions do not have to follow the Poincare-Bendixson theorem, right? We're not in the plane. We don't have Peixoto. We don't have anything saying what happens to solutions for phase spaces of dimension greater than 2. So solutions don't need to limit on a cycle or a fixed point or travel between fixed points. They don't have to do any of that because we are in a high enough dimension where they can wander. And this is the essence of chaotic dynamics. We are giving our system enough room to wander around so it doesn't have to live or it doesn't have to limit on a particular set. The behavior can actually be much more complex. But we need to show that we get there in the first place. We need to show that we're ruling out every kind of dynamics that we could possibly get to, or that we know is not chaotic. So here comes step 2. We need to show that volumes contract. So we need to show that once we get into this trapping region, we shrink wrap around the butterfly. So let's go ahead and do this. We need to show that the Lorenz system is dissipative. So volumes, no matter where you are in the system, tend to shrink as time goes on. Right? Particles like to get closer together. Man, that sure sounds like what we were talking about with Duloc's criterion. And as it turns out, that's exactly what we're going to do. We're going to wind up using the divergence theorem in order to show this. So a little bit of setup. Let's go ahead and suppose that we had some time-varying region, omega, living in R3, and it has a boundary surface, S of t, that changes in time, and it contains a certain volume, call it V of t, at time t. And we're going to see how the Lorenz system changes the shape of this region, omega, right? This is an ensemble of particles whose behavior we would like to analyze, and we're going to go ahead and flow the entire volume, this entire omega set, forward in time, as if each point inside the omega region was its own initial condition. And we do it all at the same time, and we see that this volume is either going to expand, contract, or kind of warp in some way. And we have the following picture. This is actually courtesy of Strogatz, so I should say so. Right, so thank you, Steve. Right, so this comes straight out of Strogatz. Credit where credit is due. So if n hat is the outward unit normal vector field, so I do need to specify that this is unit now, and this is the outward unit normal field for this surface S, then we can see that the change in volume, this is going to be what happens to the volume between t and t plus dt, a very small change in time, is going to be given by this kind of disappointing Easter egg or Easter bunny chocolate, right? So if you go to the store, you pick up a chocolate bunny for Easter, and you bite into it and you say, oh, this was going to be a solid chocolate bunny. No, and you get the really disappointing one where it's all really hollow. So you just get that tiny little thin chocolate layer. That's exactly what's happening in here. It's dark shade of disappointment. So the darker shaded region is this change in volume over a short amount of time. And that volume can actually be computed if we chop up S into a whole bunch of little panels, little area panels, and then give them some thickness. The thickness will be given by how much the vector field wants to push that surface between time t and time t plus dt. So that's given exactly by this flux vector, or this flux scalar field. There it is, of f dot n, and we're going to scale it by dt. So what we wind up having to do in order to figure out the total change in volume is to sum up over all these little patches on sigma and multiply them by their respective heights. And the limit, as these patches grow arbitrarily small, right, they're going to be infinite or countably infinite in expanse if we do this in the Riemann way, or in count. Yeah. So these patches grow arbitrarily small, and the limit is given on the right-hand side as a surface integral. And I can go ahead and divide through both sides by dt, and I wind up as with a limit on the left-hand side as well. As dt goes to 0, that I wind up with the derivative. The change in that volume on the left-hand side is going to be given by what happens on the right-hand side, and that right-hand side is just a flux integral through the surface, s of t, and I can apply Gauss's theorem, the divergence theorem, to the right-hand side to change that flux integral through the surface into a triple integral over the interior, which we've already named. That's the omega. So in the Lorenz system, we just need to figure out what's the divergence. And it turns out that the divergence here is actually constant. Lucky us. So if we have a constant divergence, we go ahead and apply that to the right-hand side, so the divergence actually factors completely out of the integral, and we just wind up with some negative constant times the volume of the region. So dv dt is equal to a negative number times v itself. That's solved by an exponential, a decaying exponential. So the volume of omega t must be decreasing over time. In fact, it must be decreasing to 0. So if we begin with the entire volume that's contained by the ellipsoid that we made upstairs, that sigma, then we can go ahead and define this set lambda to be the limiting object of the volume of this omega under the Lorentz flow. So this object will eventually have 0 volume, and the omega limit set of the Lorentz flow of any initial condition by our analysis upstairs says that the omega limit set must live within this set lambda. And lambda, we're going to go ahead and call the Lorenz butterfly. The last thing that I want to say about with regards to this deeper analysis is to rule out the kinds of deterministic behavior we already know. So much like we were trying to rule out limit cycles back in chapter 7, we're going to do exactly the same thing here, trying to rule out the fact that we don't have chaos. So I claim that there are no quasi-periodic orbits in the system. If there were, they would have to live on a torus, and that torus could not change volume over time, which would contradict the fact that we just showed that volumes must contract. So, in other words, there can be no quasi-periodic orbits in the system, because otherwise that torus would have to shrink. Can't happen. Second, there are no unstable fixed points or limit cycles in the system. Why? Because in small neighborhoods around these fixed points or limit cycles, the volumes would have to expand to account for that repulsion. And again, this contradicts volume contraction. So that major theorem there, that major proposition that volumes must contract, is actually really important for this system. We need to guarantee that things are limiting on a very particular set, or that we get very particular kinds of behaviors. So in particular, our analysis here at the end says that instabilities that we've already encountered, like the saddle points, they must be saddle-like in behavior rather than true unstable fixed points. Right? We need to make sure that whatever volume is expanded along an unstable manifold is also contracted, perhaps even more so, by the stable manifold. So that leaves us with the following question: what is lambda? And is the Lorenz system chaotic on that set? The answer to both of these questions, the answer to the first question should be that this really shouldn't be a surface, because otherwise we could apply Poincare-Bendixson and we'd get limit cycles, which we don't see. So it can't be a surface. And yet it can't be a volume because volumes contract. So lambda is this zero volume object. So it's not a surface and it's not a volume. So it's got to be something seemingly in between. We'll discuss that in a little bit. And the Lorenz system, is it chaotic? Well, we're going to have to establish exactly those features on this set. Right? We're going to have to actually apply the definition of chaos to that set sigma. And we will do that in the next